Previously, when we learned how to graph polar equations, we noticed that our resulting polar graphs, some of them actually demonstrated some types of symmetry. If we look at the first two graphs we graphed at the beginning of 9.7, this first one that we see here, this is known as a limaçon. And clearly we can see here that this limaçon actually has some symmetry with respect to the angle theta is equal to pi over 2. If we think of this in rectangular terms, this would be similar to us saying it's symmetric with respect to the y-axis. Let's take a look at this second graph here. This second graph is what's known as a rose curve, right? Or rose petal curve. And in this graph here, we can actually see that it demonstrates a couple of different types of symmetry. Again, this one is also symmetric with respect to the angle pi over 2. But we can also see that it's symmetric with respect to what we call the polar axis. And in rectangular terms, we think about this as our x-axis. And finally, it's also symmetric with respect to the pole. Again, the pole being the origin. So this is like being symmetric with respect to the origin. So it demonstrates three different types of symmetry there. What I want to do now is actually talk about those three types of symmetry and discuss a couple of quick symmetry tests. How do we know whether or not a polar equation is going to be symmetric with respect to a particular line or axis or pole? And how can we check that algebraically without having to graph it? So let's take a look at the first one. When a polar equation is symmetric with respect to an angle pi over 2. Well, what are we looking at here? This is like us saying the following. If we had some point here, which we'll call r theta, and so we'll just say that this is our point here, r theta. It's got some value of r, some directed distance from the pole, and it's got some angle theta. Well, if any point on this polar equation or this polar graph is symmetric with respect to pi over 2, that means this following point here, let me just graph this in a different color, this point here also has to exist. Well, how would I be able to describe that point or define that point? I can use the same directed distance of r, but that angle would have to be the supplement of pi and theta. In other words, I would say that this is pi minus theta. Another way of describing it also, if conversely, we could also say the following. We could say, well, let's use the opposite value of r, which would give me something that is just reflected over the pole. But what if we used it to describe negative theta or negative theta here? In other words, let me actually just change that color. What if we use this? Let's make that red so we can see it matching up here. We can also describe that point using negative theta. Oops. And then take this point here, which would now be r negative theta, and then by making r negative, we would flip it over the pole and we would arrive at the same spot. So that's another way that we would show symmetry with respect to the line theta is equal to pi over 2. So, in other words, if we want to check to see if a polar equation is symmetric with respect to theta is equal to pi over 2, what we would need to do is we would simply replace r and theta by either one of the two following, by either negative r, negative theta, or r, and this is the first one we described, pi minus theta, or the supplement of pi. If we get a if we get an equivalent equation, so if equivalent equation, then we know it's symmetric. And we'll talk a little bit about what that means to have an equivalent equation, because it doesn't necessarily mean that it's going to be the same exact equation, but we'll talk a little bit more about that in just a bit. Now let's look at the next one. How to check to see if something is, or a polar equation is symmetric with respect to the polar axis. So again, if I have some point here, r theta, right here, and if it's symmetric with respect to the polar axis, which is this axis here, well, think about it being symmetric with respect to the polar axis. That means we're flipping it over this axis, and so we would have to have the following point here. So how could I describe this point? Well, one way is to use the same value of r, same directed distance, but if this angle was negative theta, that assumes that our first angle was positive theta. So if we had some angle of theta, we simply just find negative theta, and we would have it reflected over the pole. So that's one way. Or we could also say something similar to what we did before. Negative r and a supplement. Let's just clean that up just a little bit. Of theta. And just think about that for a little bit and just see how that would make sense for you. So what we could do here is, similarly, if we want to check to see if a polar equation is symmetric with respect to the polar axis, where again, we're going to replace r theta by the following. R negative theta or negative r pi minus theta. One of those two. And again, this next part here that we get, if we end up with an equivalent equation, then it's symmetric. I'm just going to go ahead and copy and paste this. That's going to be the outcome for all of these tests. So we'll just say that here. Okay. Now, final one. How do I know if a polar equation is symmetric with respect to the pole? So again, let's go ahead and let's plot some r coordinate, r theta coordinate on a polar equation. So this would be our point over here. If this is our angle theta. And if it's symmetric with respect to the pole, what that means is that this following point here has to exist. Remember, this is like being symmetric with respect to the origin. So think about how we could come up with a polar coordinate here. One way is to say negative r theta, right? So again, the same angle of theta, but by making our r value negative, we're flipping it over the pole. Or what could I do to the angle in order to give me a value that, or a coordinate that is reflected over the pole? I could just go ahead and add pi. So then this would give me r comma pi plus theta. So that's another option. So you kind of get this sense of what we're going to do by now. If I want to check to see if a polar equation is symmetric with respect to the pole, I'm going to go ahead and I'm going to replace r theta by negative r. So just flip the r for a negative r. Or I could take that r pi plus theta. And just like we did before, we're going to go ahead and we are going to say that if we end up with an equivalent equation, then we know that it is symmetric with respect to whatever we were testing for. And again, we'll do this in just a bit with some practice problems. The last thing I just wanted to mention in this introduction is that there are a couple of quick symmetry tests, things that you don't necessarily have to show the work for. And the ones that we can state just right off the bat is the following. We can say that if r is some function of sine theta, some function of sine theta, then we can say right away that that graph is going to be symmetric with respect to theta is equal to pi over 2. It is not saying that it is exclusively symmetric to that, meaning it could be symmetric to some other components, whether it's the polar axis or the pole, but we know for certain that if it is a function of sine theta, if r is some function of sine theta, it is indeed going to be symmetric with respect to pi over 2. There is one exception to that, and I should point this out so that I don't get questions about it later. The one exception to that is lemnis gates. And only because lemnis gates deal with polar equations that have r being squared. And so that gives you a couple of different options. So the simple quick symmetry test of simply saying that r being a function of sine theta gives us symmetry over pi over 2 doesn't necessarily apply with lemnis gates. Now, the other quick symmetry test that we should also be aware of is our polar equations that involve cosine of theta. So if r is some function comprised of cosine theta, then we can say that it's symmetric with respect to the polar axis. And one way to kind of just remember the two of these is think about the polar axis in rectangular terms. It's like the x-axis, so think of x being cosine. If a graph is a function of sine theta, then think of sine again being associated with y, and we think of the y-axis being the rectangular terms for theta is equal to pi over 2. So cosine goes with x, sine goes with y. And so that's just one quick way to remember those two quick symmetry tests. So in the next section, I'm going to do a couple of practice problems, and we're also going to continue to talk about finding zeros and maximum R values of